Number 13, looking at an example of conditional probability. And this is in 3.2. It's the probability that an event is occurring when we're given that another event has already occurred. And for part A here, we're finding the probability that a randomly selected student is male, given that that randomly selected student received a business degree. So click to pull the table of data up here. And since we're given that the student received a business degree, we're really only looking at this first column of data. We know the student has a business degree, so this is the total number of people it could be, and we want to know the probability that that random person is a male out of that total number of people. So you would put the number of males with the business degree over the total number of business degrees and just do that division, and you get your probability. For part B, another conditional probability, the probability that a randomly selected student received a business degree given that the student is female. So since we're given that they're female, that's the condition, we're only going to be looking at the female, so only the second row in the table. And so the probability on that second row that they have a business degree, it's the number of female business degrees over the total number of females. So business degree females divided by total number of females, and do that division to get the conditional probability value. Number 14 is a conditional probability like number 13. And so click on your table to see the survey results. And part A here, we're going to find the probability that a randomly selected worker contributes given that the worker is male. So since we know they have to be male, we're only looking at the males. And so that's the first row here in this table. And so we want to find the chances that they contribute out of the total number of males. And so do that division there, the 107 divided by 250. And that division will give you then the probability. For part B, find the probability that a randomly selected worker is female and we're given that they contribute. So since we're given they contribute, we're only looking at the people who contribute, which is this first column here. So out of that total who contribute, we want to know the probability that they're female. So we'll do that division, and it will give us the conditional probability result. Number 15, classifying two events as either independent or dependent. And in 3.2, you can see the definition of what it means to be independent. It's when the occurrence of the one event does not affect the probability of the other event. And if the events are not independent, then they are dependent. For this one, we have randomly selecting a city in Texas and randomly selecting a county in Texas. Since these are just two random selections and it doesn't matter what we pick for the city, it's not going to affect the random selection of the county. They're both random processes. We have independent events. Whatever we do for the first one, however that outcome is, it's not going to affect the other outcome. So we have independent events. Number 16 is like number 15. We're determining if two events are independent or dependent. So independent, the probability of the one event does not affect the probability of the other one. And dependent, the events do affect each other's probability. So our first event is returning a rented movie after the due date. And the second event is receiving a late fee. And if you have any experience with renting movies, you know these events are dependent. If you return the movie after the due date, your probability of getting a late fee goes way up. And so the probability of receiving a late fee is definitely affected by when you return the movie. So we have dependent events. For number 17, we are finding the probability of two events occurring in sequence. So we're going to be using the multiplication rule. And as the name of the rule suggests, we're going to be multiplying probabilities here. One key to always remember with this rule is you're going to have the two events. You multiply the probability of A times the probability of B. but you have to consider whether the probability of B has changed because A has already occurred. So there could be some conditional probability when you look at that second event. In this example, we're drawing two cards, and the first card is not replaced before the second card is selected. So the probability of selecting an 8 would be 4 out of 52. There are 52 total cards in the deck, 4 of them are 8s, and we're going to multiply that by the probability of the second event. And our second event here is selecting a 6, but remember the card has not been replaced, the first card we drew. So our conditional probability of getting a 6 is 4 out of 51, because there's still 4 6s, but there is only 51 cards in the deck now because we drew a 1 card already. So if you multiply those values together, you'll get your final solution and convert it to a decimal with the right number of decimal places. Number 18, like 17, we're going to use the multiplication rule because we have two events occurring in sequence. Here we have a sample of 1,000 people, and a certain number of them think celebrities are good role models. So 2 are selected at random without replacement. So you pull the first person out, and then out of the remaining 999 people, you pull another person out. So find the probability that both adults think that most celebrities are good role models. So there were 189 total in our sample that thought they were good role models. And so when we randomly select that first person, this is the probability that the person thinks they're a good role model. And now since one person has been removed, to get that second person also thinking celebrities are good role models, there would only be 999 total people left in the sample because one's removed, and there would only be now 188 who think celebrities are good role models. So multiply those two values together to get the probability. For part B, we're finding the probability that neither adult thinks most celebrities are good role models. So the problem just tells us how many do think they are good role models, so we need to do subtraction here. 1,000, our total sample size, minus how many do think they're good role models, would leave us with 811. So that must be the amount who think they're not good role models. So I've written that up here. The two amounts need to add up to the total in our sample, in this case 1,000. And so we still have the 1,000 people to pick from with our first random selection. This is the amount who don't think they're good role models. And after we've selected one, now there's only 999 people left, and our top number has gone down by 1 as well. Multiply those together, and it will give us the probability that we're looking for. In part C, the way you want to do this is use your previous answer you just got for part B. So in part B, we found the probability that neither person we selected thought celebrities are good role models. So if we think about all the possible outcomes when we're selecting two adults at random, like we found in part B, they could both say no, the celebrities are not good role models. The first person could say yes, the second person no. The first person no, the second person yes. Or like we found in part A, both people could say yes, celebrities are good role models. So there's 4 possible results. The 4 results have to add up to 100% because this is 100% of the possibilities. So one way to solve C would be to find the probability of these 3 results where at least one person is saying yes and add those 3 results together. The quicker way is to use the complement. If we just found the probability of this in part B, and it came out in our example to 658, then the other 3 must add up to the value that will make the sum be 100% or 1 if we're working with decimals. So just do 1 minus the result of neither person thinking celebrities are good role models. So 1 minus 0.658, and then that will give you the probability of at least one person of the 2 adults thinking celebrities are good role models. Number 19 is a multiplication rule like we've been doing in the last few. And so the first event, the doctor gives a patient 90% chance of surviving a surgery after a heart attack. Now, if they survive, then they have a 20% chance that the heart damage will heal. So we want the probability of those two events together. Find the probability the patient survives the surgery and the heart damage heals. So we're going to multiply those probability values together for our two events. And the result of that multiplication is the probability we're looking for.